Simple ket addition in notation. So you see here a ket u, which is a column vector. This is what's normally seen in quantum mechanics. Again, this is three available states, values related to quantum mechanics. So three elements. We can have 3 elements. We can have 5 elements. We can have 10. We can have 10,000 elements. So simply what that is. As mathematically, if that we a bra, it can be transformed into a row vector, which is this right here. Here's the row vector. Now, when you do an inner product with a row and vector and a column vector, thinking in terms of quantum mechanics, it's not necessarily normalized. So here's an example of it not being normalized. So when I multiply these two together, I get a 26 plus 26x squared. If, let's say, we want to normalize it, the module is defined this way. So we can calculate the module by taking the square root of 26x squared, which is the inner product, which is square root of 26 times x. Now, if we want to normalize, what is the normalized value? Well, the module has to equal 1. So in order for 26 times x to equal 1, x has to be 1 over 26, square root of 26. And we have a new, unnecessarily similar eigenvector or column vector, which is what we have here when you do the normalization. Now, if we want to check and make sure that the eigenvector is not eigenvector, but the ket is normalized, we multiply it by its bra. And I did that and did the math, and this is equal to 1. Very simply. So the column vector is normalized. So when you dealing with quantum mechanics, normally, especially in matrix representation with these discrete states, you have to make sure, one of the things you make sure is that your ket is normalized, even with the continuous version with the integrals. If you have integrals state functions, they call them, well, you have to also make sure those are normalized, because probability is what is dealt with in quantum mechanics. When you make a measurement, what is that measurement going to probably be? What are the chances of that measurement, if you measure that light at that time, and it being moving quantum mechanically, what is that measurement? What is it doing at that time? If you measure it again, it's not necessarily that you're going to get that same value. Maybe it's a probability that you will get a different value, but there's also a probability you get that same value again. So just to give you a little bit of the reasoning behind why things are handled the way they are handled, because there are these, you have continuous values, so you have You can have a value from negative infinity to infinity, which is continuous. But quantum mechanically, you can have only certain values. You limit it to certain values, discrete values. Now, another thing about it, what a lot of people have problems with the notation is that, uh, or the notation can be kind of weird. Is here's another example about the notation, which I have two um, kets with a basis. The basis with basis kets U1, U2, and U3. These are bases. So here's another ket with the same basis, um, just like a vector. Vector has a basis. A vector has a basis. So simply you can have, say, you have a vector and you have I plus j plus k, which these are orthogonal. So if you take the dot product of the unit vector I, you're going to get 1. If you take the dot product of I and j, you're going to get 0. It's the same situation here. Now, the whole point of this is the fact that you, what in the world is this here inside? Why are they doing this? They play with these notations, and you look at different quantum mechanics books, uh, you have to be careful. What is the interpretation of this? Because they don't really make it obvious a lot of times. What are you doing here? So when you put two eigen two kets together, two states together, this is what they're talking about here. You have the same basis, kets U1, U2, U3, but you're just adding the uh, each number in front of the kets, and you get an answer. It's the same thing with the subtraction. So you see the difference in the addition. So normally, when quantum mechanics is introduced, it they don't go to this detail. It's just some kind of abstract mathematical calculation, and you're being told as a student that oh well, you're supposed to know this. It's from linear algebra, but linear algebra doesn't typically share this notation. Yeah, you know what a vector space is. You know this is about vector spaces, but there in mathematics is a different notation. In mathematical physics / quantum mechanics, the notation is different, which is what we have here. That's what we have here. So we have to really understand what's under the hood on this, because it slows you down from doing the process of you're trying to study a system, whether it be something a small particle or quantum light or whatever system that you're studying. You need to be able to smoothly navigate to get to where you need to get measurements, get answers, uh, to not have to be bogged down with the abstract mathematics. That's what the way this course is taught, that a lot of people get the mathematics kind of overrides the quantum mechanics, the physics. The whole thing of this is to get to the physics. It's not the math. So I just want to make that point. This is a short video with some scratch work, some small things to think about that turn out to be big, because when you go through and do the calculations, you don't have to worry about all this. There are some people that this doesn't bother and have a problem with it, but this uh, this detail, people don't really see how easy this math is once you look under the hood. So This is Alpha Math Scientist. I hope this video helps. Please subscribe, share my channel. Uh, I'm hoping to continue to bring uh, more possibly helpful content. I'm open for suggestions, but I am mainly right now focusing on trying to put physics related and math related content up that uh, things are not normally discussed that will be helpful to the student or even helpful to a researcher or whatever. So hope this helps.